All right, good morning, everyone. So it seems like I'm having internet connectivity issues with my iPad at least. So I'll just have to verbally tell you what the questions are as we look at examples. So just to kind of remind you of what we've been talking about. So on Thursday, we talked about the force on a current carrying wire in an external magnetic field. And what we found was that the force is then equal to the integral over the differential length of the current then times the differential length crossed then by the external magnetic field. Now the top one is good if the external magnetic field is not constant or if the object is curved. Remind you quickly of what DL is. So if here's my wire, say doing something like this, then again DL is a small section cut out from the wire. Let's say this thing has current running through it, got the current in this direction, then DL points in exactly the same direction as the current. So in this case, DL would point in this direction. So it points in the instantaneous direction of the current at that particular point. But if my wire is straight and the external magnetic field is constant, in that case, it simplifies to simply this guy, which is then the current crossed by the length crossed by the external magnetic field. So in this case, here would be my straight wire, something like this. Current, say, would point again, let's point it in this direction. So here, remember, L is a vector, which is the length of the object, whose direction points in the direction of the current. So this is L, so that the magnitude of L here is simply equal to the length of the object. So this would be my length. And then B would be some external magnetic field. Let's say it points off in this direction. So this is B. So if I wrote this as a magnitude, so F of B magnitude then would be equal to ILB times sine of the angle between the two, where the angle is specifically the angle between the current and the external magnetic field. So this would be my angle of theta. So good. So last time we looked at an example, if we had a straight wire and then constant external magnetic field. So we're going to look at today is what happens if we don't. So let's do an example of that. So this thing is not working, so I'll tell you what the example is. So basically what it says is that we have two straight wires. So here's my two straight wires, connected then to a semicircular loop of wire. So here's my semicircle, which has a constant radius of R. So here I have current running through it in the counterclockwise direction. So my current is going in this direction. So this is current, meaning it's coming up through the right wire here, through my semicircular arc of constant radius of capital R, and then down through this portion of the wire. And all sections then have exactly the same amount of current running through them. Now what I want to know then is, at the center point here, let's call that point C, not at the center point, what am I talking about? What I want to know then is, what is the force on the wire? Thinking of a different problem. So I want to know, what is my force on this wire? So this is what I want to know. And here we're told that we have an external magnetic field. Let's say our external magnetic field is pointing out of the page everywhere, and this guy is equal to simply a constant. So this is my external magnetic field. And we know this guy is simply equal to a constant. So in this case, I want to know, what is the force on this entire wire? So how much force is this wire actually feeling? So good. So let's talk about each part first. So we can imagine then is that this thing is split up into three different configurations. So we're going to have the force on the right wire, the force on the left wire, and then the force on the semicircular loop, which means that our total force then, FB, is going to be equal to the force on the right wire plus the force on the left wire, plus then the force on the semicircle. So this is going to be our net force. Now, let's talk about each one of these forces. So here and here, these are simply straight wires in a constant external magnetic field. And since they're straight wires, what that means then is that what? The force on this guy and the force on this guy will be determined by that second equation that we wrote down, which is IL across B. Now, again, to determine the direction of force, let's look at that first. We have to use our right-hand rule. Remember, our right-hand rule says that we're going to point our fingers in the direction of the current, curl them in the direction of the external magnetic field, and then that gives us the direction of the force. So here, this is my direction of I. So I'm going to put my fingers in the direction of I. Since V is out of the page, I got to rotate my palm away from the board, curl towards the external magnetic field, which means the force on the right wire is pulling it this direction. So for force right, let's write that down first. This guy's going to feel a force in this direction. For force left, current is now downwards. I'm going to point my fingers downward. But again, my external magnetic field is out of the page. So I rotate my palm so it's pointing out of the page. Curl towards the external magnetic field. So my thumb now points in this direction, which means that now the force on the left wire is going to be pulling in this direction. Now, from here, what we can see is that the force on the right wire and the force on the left wire are opposite in directions. What about the magnitude of those two forces? Well, for each one of these two, again, we're going to use that F is equal to then what? IL times B times sine of the angle between the two. Let's look at the magnitude of each one of those guys. For this guy, this current here is the same as this current here. This length here is the same as this length here. This external magnetic field here is the same as this external magnetic field here. So what can I tell me about then the magnitude of the force on this wire versus the magnitude of the force on this wire? They're the same. So what's going to happen then is what? The force on this wire is equal to the force on this wire, just in opposite directions. So when I vector sum this force with this force, what does that give me? 0. So the sum of these two is simply going to be 0. Because these guys are simply equal and opposite from each other. Which means that the total force then, acting on this wire, is simply going to be the force from the circular loop. Is okay? Now, what's the direction of the force? Well, again, here we would point our fingers in the direction of the current. So this is the direction of my current, say at this point. Curl towards the external magnetic field. So here my thumb would point this direction. If I follow that all the way through, my thumb is going to make an arc doing something like this, which means what happens to all the horizontal components of the force? So if I'm putting my thumb like this, starts off here, and then does this, what happens to all those horizontal components? They all cancel, which means the total force on this is only going to be the upward pull on it. So my total force from the circular part is only going to be in the, say, vertical direction. Good. So last thing I need to know then is what is the magnitude of this force? So let's look at the magnitude of the force. So we know the force then of the circular, magnitude-wise, is then going to be equal to the integral of the current times dl crossed by b. So let's look at this guy. So what are these things? Now, since I'm looking at the magnitude of this, let's look at the magnitude of this guy. So this is going to be equal to then the integral of I times the magnitude of dl, which is simply dl, times the magnitude of b, which is b, times then sine of the angle between the two. Let's call that angle theta. Now, let's switch back to our picture. So let's draw a dl. So let's say here's my dl. My dl in this case is going to point this way. So this is my dl. My external magnetic field is pointing out of the page, which means at any point along this path, what's the angle between dl and the external magnetic field? So dl is doing this. And b is pointing this way. What's the angle between the two of them? So b is this way. dl is doing this. At any point along here, you do that in front of the camera. So dl is doing this. Any point along this trajectory then, what is the angle between the dl and the external magnetic field? 90 degrees. So in this case, the nice thing about this is theta is simply equal to 90 degrees, which means this thing becomes the integral of I dl/b. Now here, the current is simply constant, doesn't depend on dl, so I can pull that out of the integral. The magnetic field is also constant, since that is in an external constant magnetic field, so it also doesn't depend on dl, so we can simply factor those guys out as well. So this guy then becomes simply I times b times the integral then of dl. Well, what's the integral of dl? Well, the integral of dl is simply going to be the length of this semicircular loop. So good. So I know that dl, this is going to be simply then I times b times L. But L for us is going to be what? What's the length of half an arc? Good. Or pi times r. Good. 1/2 of 2 pi r is pi r. Good. So this guy is simply going to be equal to what? I times b times pi times r. So this is our force. So in this case, our force then is simply IB pi r. It's okay? Good. So the next thing I want to talk about is what happens then for a single charged particle. So again, what we have here is, here's our wire. Our wire is carrying current. So let's say our current is pointing in this direction. So here's my current. And what we said is that on this guy, the force then is simply equal to IL cross B. Well, remember, what is current? What is current? Moving charges, right? Which means that even though I have a current here, what this means is on the inside of the wire, I also have simple moving charges. Each one has a charge of Q, moving, say, in this particular direction. So what this means then is if the wire feels a force because there is charge moving inside of this external magnetic field, since the wire then feels a force, what that means is that the force is actually derived by the fact that there are individual particles inside of this wire which are also feeling a force. So what this means is every single one of these charged particles in this external magnetic field then feels a force. So what's really happening is that the wire itself doesn't really feel a force, but the charged particles are feeling a force, which manifests itself by the wire feeling a force. Does that make sense? So from here then we can ask, well, what is the force on an individual particle? So let's ask that. So what then is the force on each particle? Well, to do that, we know that current, by definition, is equal to the change in charge divided by the change in time. So I'm going to rewrite this then as the change in charge divided by the change in time. Each one of these particles, though, is moving with a velocity of v. So this is my velocity v, which means in the time frame of delta t, this particle here actually moved this total distance of length L. So in the time frame of delta t, this particle here started off at this point, but moved to this point in the time frame of delta t, which means it has moved the length of L. Which I know then at L is going to be equal to the velocity at which it's moving times the change in time. So let's plug that in. So this is now going to be also times the velocity times the change in time crossed by then the external magnetic field. Now what happens to the two delta t's then? They're going to cancel. So I can write this then as the change in charge times the velocity crossed by the external magnetic field. But inside of this section, delta Q is actually the total number of particles times the charge of one of those particles. So finally, I can write this as N times QV cross B. So this is our force. So what this says is that the force actually acting on the wire then is equal to the force on one single charged particle times N, where N is the total number of particles moving inside of this wire. That's what this thing says. So from here, we can then say, well, the force on a single charged particle then is simply this quantity. So what this finally tells me then is that the charge, or the force on a single charged particle then is the charge of the charged particle times its velocity crossed by then the external magnetic field. So this is the force on a single charged particle. Here, again, if I want to look at the magnitude of the force then, F of B, would then be equal to Q times V times B times sine of the angle between the two, where here the angle is specifically the angle between the velocity and the external magnetic field. So this is the angle of theta. Now, one thing to note here, different than what it was for the force on the wire, here we have to be a little bit more careful because the sign of a charge can be what? It can be negative, can be positive, and it can be zero. Right? So first thing we can tell from this is that the force on an uncharged particle in an external magnetic field has to be zero automatically because the charge is zero, so in that case there is no force. But since the charge can actually be negative, what that means then is when we use our right-hand rule, because the way that we read this is the same way we do it before, according to right-hand rule number 2, to determine the direction of the force, we point our fingers in the direction of the velocity, curl towards the external magnetic field. But if the charge is negative, we have to do an extra rotation by 180 degrees. So if I'm dealing with something like an electron, if I point my fingers in the direction of the velocity, curl towards the external magnetic field, my thumb now gives me the wrong direction because the charge is negative, so I have to rotate my hand by an extra 180 degrees to get the right direction. Okay. So when it comes to negatively charged particles, there's one extra step where we have to rotate our hand by 180 degrees. So just note this extra complication. So if Q is less than 0, then step 4, rotate hand by 180 degrees to take it into account. Now, if you are extra savvy with math and you are okay with different right-hand rules, in this case, you would actually use left-hand rule number 2 instead of right-hand rule number 2. If you use your left hand instead of your right hand, it'll actually give you the right answer. If you're not comfortable with that, right-hand rule number 2, rotate with an extra 180 degrees. So I'll put an extra little asterisk here. You can use your left hand here. So anytime that you are using this rule here where the charge is less than 0, in that case you can use your left hand instead of your right hand. That will automatically give you the right answer. But if you don't want to confuse yourself, you always want to use your right hand, which is probably better practice. Just remember, always rotate by an extra 180 degrees. So good. So let's do an example. So this example says, again, I'm having internet issues. So this says that we have an electron, so here's my electron, moving in an external magnetic field, which has a velocity, so the velocity of the electron is 2 × 10⁷ meters per second. And this thing is moving in an external magnetic field, which is perpendicular to the direction of the electron. So here I'm going to say that it's pointing outward, where the magnitude of the external magnetic field is 0.01 Tesla. So what we want to do in this case then is simply describe the motion of the particle. So we want to describe the path of the electron. So this is what I want to do. Actually, I'm going to move this down a little bit. Put it here. This is E, moving in this direction. E, 2 × 10⁷ meters per second. So we want to describe the motion or the path of this particle as it moves through this external magnetic field. So before we write down anything mathematically, let's figure out what it's actually doing. So let's apply now our right-hand rule. So again, here we will put our fingers in the direction of the velocity, this one. Curl towards the external magnetic field. So in that case, I have to rotate my palm away from the board, curl towards the external magnetic field, which means the force will be downward, but it's a negative charge, so we have to rotate our palm in the actually other direction. So the force in this case is actually going to be upward. Okay. So at this moment in time, this thing is feeling a force upward, which means that the particle is going to start to curve up. So at some later time, this thing is going to curve to this location. What happens at this location? Well, at this location, it now has a velocity vector pointing in this direction. This is my velocity vector. So let's do the same thing. So again, we're going to point our fingers in the direction of the velocity, curl towards the external magnetic field. So I'm going to rotate myself this way. So my thumb would point down in this direction. But again, it is a negative charge. So I'm going to rotate back this way. So now my thumb is pointing in this direction. So now, at this moment in time, the force is now this way. Which means it's going to continue to arc. So let's continue arcing. So this guy's going to keep moving, and now it's going to be here. What about at this point? Well, this point, my velocity vector now points this way. So let's do the same thing. So again, I'm going to point my fingers in the direction of the external magnetic field, or sorry, direction of the velocity, curl towards the external magnetic field. My thumb should point this way, but since it's a negative charge, I got to rotate this way. So my thumb at this point points this way. So now my force is pointing this way. It's going to continue the curve. What type of path is this thing following? So if I keep up this, the direction is always, the force is always going to point towards where? To the middle point. Which means this thing is always going to do a circle. So here, what's going to happen then is as long as the velocity of the vector points perpendicular to that of the magnetic field, this thing is always going to move in a circle. The path that this thing is going to follow then is going to be circular. What happens to the velocity? Does the speed increase or decrease? Or does it remain the same? Well, let's say, what direction is the acceleration compared to the direction of the velocity? So at this moment, if my velocity is this way, my force is this way, what's the direction of the acceleration? This way, same direction as the force, Newton's second law. At this point, velocity is this way, acceleration is this way. At this point, velocity is this way, acceleration is this way. So the acceleration is always perpendicular to that of the velocity, always. So not only is it moving circular, but the velocity is always perpendicular to the acceleration. If the velocity is always perpendicular to the acceleration, can I increase the magnitude of it or decrease the magnitude of it? I can do neither. The magnitude of the velocity stays the same. The only thing that happens is the direction changes. So the other thing I note from here is that the magnitude is equal to a constant. So I have something moving in a circle with constant speed. What do we call that? Going all the way back to 205. What's that called? That's the same thing as this. What was this called? Remember? And again, I know my velocity tangent because if I do that, here go my keys. What do we call that motion? Go ahead, Zach. Centripetal acceleration with uniform circular motion. Great. So this is uniform circular motion. Which means exactly as Zach said, the acceleration is actually equal to centripetal or radial acceleration. Fantastic. So what will happen then is as long as the velocity is perpendicular to the external magnetic field, this thing will move in a circle. It will move in a circle such that the velocity stays constant. The acceleration is perpendicular to the velocity, which means it has to be centripetal acceleration. Which means that this thing will move in a circle of some fixed radius because the radius stays constant. So overall, this thing is going to move in a circle of constant radius. So the next question we can ask ourselves then is, what is that radius? What is that radius in this case? Now, one quick question. We did this for a negative charge. What would happen for a positive charge? Would it do the same motion? Good, Richie. Yes. But what would be the difference? It would circle in the other direction. Great. So here, this is an electron. If I had a proton instead, these are color I haven't used yet. There's no color I haven't used yet. We'll use black. There we go. So if I use the proton instead, it would actually circle around in this direction instead. So if this was a proton, the velocity would change in this direction. It would actually go clockwise downward as opposed to the electron, which is going to go counterclockwise upward. That would be the only difference. So good. So the next thing we're going to ask then is, well, what is the radius of curvature? What is the radius of this circle? So good. So Newton's second law says that the sum of the forces acting on our particle then is then equal to, since this is uniform circular motion, mv squared over r. Because remember that centripetal acceleration is the velocity squared divided by the radius. So here, the only force which is acting on it is the magnetic force. So now I get the magnetic force then is equal to mv squared over r. Since this is a single charge particle, the magnetic force then is going to be the charge of the charged particle, which for us is the fundamental charge, times the times the velocity, times the external magnetic field, times sine of the angle between the two is then equal to mv squared over r. Everyone's okay? Now here, what's the angle? So here, again, my velocity is moving in a circle, so my velocity is only doing this. External magnetic field is pointing this way, so what's the angle between the velocity vector and the external magnetic field at any position? 90 again. So here, theta is simply 90 degrees, so this thing becomes EVB is equal to mv squared over r. This velocity cancels down one of those, so let's go ahead and cancel that out. So finally I get that E times B then is equal to mv divided by r, which means then that's what? The radius is equal to mv divided by EV. So here, this is the mass of the electron, so this is 9.11 times 10 to the minus 31 kilograms times the velocity, which is 2 times 10 to the 7th, divided by the fundamental charge, which is 1.6 times 10 to the minus 19, times my external magnetic field, which is 0.01. Plug all those in. Right, in this case then is our radius works out to be 1.1 times 10 to the minus 2 meters, which is 1.1 centimeters. So as long as this electron, in this case, is moving at 2 times 10 to the 7th meters per second in an external magnetic field of 0.01 Teslas, the radius then is about 1.1 centimeters. So this is my radius. Well, we can go further. What's the time it takes for this thing to do that? Well, that's the period. Right? So how does the period then relate to the velocity? Well, remember that from our second kinematic equation, the distance we travel, which is 2 pi r, is then equal to the velocity times the time, where the time in this case is simply equal to the period. So this says then that the period is equal to the velocity divided by 2 pi r. Well, we now know r is the same thing as what? mv divided by EB. So let's plug that in. So this becomes v divided by 2 pi times mv divided by EB, which means this v is going to cancel this v. So this then becomes E times b divided by 2 pi m. So this is the period. So this is the amount of time it's going to take for this thing to actually move in a circle. Okay? What's up, Greg? Oh, because I did math upside down. I have moments. Good. So all this stuff actually switches direction. Good. Thank you for looking confused. Okay. So this is 2 pi r divided by mv divided by EB. Good. So this becomes, sorry, I changed the wrong one. There we go. So this is mv divided by EB divided by v. Good. So those are going to cancel. So this becomes 2 pi m over EB. Good. Thank you. One of those days. Okay. Everyone okay? So this is the time or the period, but remember the period is related to the frequency. So the frequency then is 1 over the period, which is then equal to E times B divided by 2 pi m. So this is our frequency. This frequency has a special name. This is actually what's known as the cyclotron frequency. So this is called cyclotron frequency. It's called cyclotron frequency because typically what you do is you put a charged particle into an external magnetic field, which causes it to move in a circle. As it moves in a circle, it turns out that as a charged particle accelerates through a circle, it also gives off radiation. Talk about why this happens in a little while. But this is what's called an old cyclotron. These were the old types of particle accelerators. Basically, you take a charged particle, rotate it in an external magnetic field. That then gives off light, i.e. radiation. You then can collect that radiation to use basically for particle accelerators, things like that. So this is the frequency, which corresponds to the energy at which the particle is giving off that radiation. So this would be the energy of the light. So this is everything we can then say about the motion of that charged particle. So again, if I have a charged particle in an external magnetic field, as long as the velocity is perpendicular to it, it has to move in a circle. Moves in a circle of a fixed radius because it moves in uniform circular motion with a period, which is given by this guy, and a frequency, which is actually given by this guy. This is pretty much everything we can say about this charged particle. Now, one interesting question becomes then, what happens if the velocity is not completely perpendicular? So for example, let's say if my external magnetic field points this way, and my velocity vector points here, some angle relative to the magnetic field. What happens in this case? Well, what happens in this case then is the portion of the velocity which is perpendicular to the external magnetic field, that's going to be this portion, let's call that the perpendicular portion. This is actually going to cause the charged particle to move in a circle around the external magnetic field. The portion of the velocity which is parallel to it, so this portion, let's call that V parallel. V parallel doesn't feel the force because the velocity is in the same direction as the magnetic field, which means sine of the angle between the two is 0, so that velocity stays fixed. So what happens in that case then is this portion causes it to move in a circle, this portion causes it to keep moving in that same direction, which means that this thing is going to spiral. So the actual path of this thing is it's going to do this. This distance here is what's known as the pitch. So what'll happen then is that this thing will float basically down along the direction of this external magnetic field line, doing spirals that actually moves down the line. So that's what this thing actually does. Now, one interesting effect that this thing has, and hopefully my laptop or my iPad is actually deciding to work at this stage. If not, we'll just kind of wing it. One interesting side effect of this is, please work. Yay! The aurora borealis. The aurora borealis is actually made from this effect. So basically what happens with the aurora borealis is, I've got to draw a picture. Here's the Earth. So let's draw the Earth. Draw blue because it's mostly blue, water. Okay. Here's the Earth. The Earth, again, has external magnetic fields, or has its own magnetic field lines that basically do something like this. Over here is the sun, and we talked about solar winds before. So again, what happens is you get these gigantic promenades, which are magnetic field lines from the sun coming out, which then shoots charged particles moving at us with a velocity of v. What'll happen then is some of these charged particles will then move into the external magnetic field and then start to spiral around the magnetic field of the Earth. But as they start getting closer and closer to the poles, the density of the field lines by the poles becomes stronger, which means that the strength of the external magnetic field or the Earth's magnetic field increases. Which means that as the, let's go back to our slide, as the strength increases, what happens to the frequency? Well, the frequency goes up, the period goes down, and the radius goes down. So what'll happen then is as it gets closer and closer to the poles of the Earth, this radius gets smaller and smaller and smaller, which means that these guys are going to spiral with tighter circles, which means that the energy is actually going to go up. As the energy goes up, the energy of these charged particles is radiating away out to the air around it, actually ionizes the air, causes the electrons to strip off, but those electrons will go back to those air molecules, causing them to fluoresce. causing the light. So what you're actually seeing here in the aurora borealis is simply that. All the charged particles which are coming to us from the sun or from distant galaxies are actually spiraling around these magnetic field lines. And these curves that you're seeing is actually the magnetic field lines of the Earth in that local area. But they're spinning around with such a small radius, with such high energies that it's ionizing the air. The air then is recombining the electrons back to us, giving off the light. And what you're seeing is simply the electrons recombining back with the air molecules that were originally ionized. So these are the aurora borealis. Simply charged particles following the path of the external magnetic field. It looks pretty, but it's simple science. Okay? So this is kind of one interesting thing about this effect. So, okay? Not too bad. So what's another thing we can talk about? Another thing we can talk about, which will correspond to this back, is what's known as the Lorentz equation. So the Lorentz equation simply says, what is the total force on a charged particle if there's both a magnetic field and electric field present? So here we're going to have both a magnetic field and an electric field. So what the Lorentz force says then is, well, what is the total force on the charged particle? Well, the total force then is simply going to be the electric force plus the magnetic force. Going back, we know the electric force is simply going to be the charge times the magnitude or times the electric field, plus the magnetic force, where we now know the magnetic force is the charge times the velocity of that charged particle crossed then by the external magnetic field. Since those two charges are the same, let's go ahead and factor them out. So this becomes Q times E plus V cross B. So this is my total force on a charged particle moving in both. Now, the most interesting thing about the Lorentz force is we can build something which is called a velocity selector. It's called a velocity selector. So what's a velocity selector? A velocity selector is a parallel plate capacitor. So here's my parallel plate capacitor. So one side is going to be positively charged. One side is going to become negatively charged, which means we're going to have an electric field which points from the positive to the negative. So this is my electric field. But here, we then want to put a magnetic field perpendicular to this guy. So I'm going to put a magnetic field perpendicular to the electric field. So I'm going to put in an external magnetic field. So what's the point of doing this? Well, the point of doing this is if I take a charged particle, here's my charged particle of charge Q, and I send it between the plates with a velocity of V. What's going to happen? Well, let's look at my charged particle when it's here at the location where I drew the electric field line. For fun, let's say that this is a positive charge, just so we can get all of our forces straight. So this is a positive charge. What this means then is that the charged particle is going to feel a force downward because it has positive charge. It's going to feel a force then in exactly the same direction as the electric field. So this guy is going to feel an electric force this way. However, since there's a magnetic field as well, I'd have to point my fingers in the direction of the velocity, which is this way, curl towards the external magnetic field, so this way, which means it's also going to feel a magnetic force upward. So simultaneously, this guy's going to feel a magnetic force in this direction. So what'll happen then? Well, as this thing then moves between the two plates, there's going to be two different forces pulling it in two different directions. The electric field is trying to pull it down in this direction towards the negative plates. The magnetic force, though, is trying to push it to the positive plates. So the question is, what happens to the charged particle? Well, the answer is it depends on the velocity. Because if it moves in and it has a very small velocity, which one of the two forces is going to be bigger? So if I have a very tiny velocity, which force will be bigger, the electric force or the magnetic force? Let's go back to weight now. Magnetic force is what? QV cross B. So if this thing is very small, what happens to this force? It's very small. So if this thing moves with a very small velocity, this term will basically be subdominant to this term, which means then that this thing is going to experience a total force downward. So if this thing has a very small velocity, it's going to end up curving downward and maybe hit the bottom plate. What happens if it has too much of a velocity? Well, if it comes in with a very high velocity, this term now becomes dominant over this term, which means overall it's going to feel a force upward, which means in this case it's going to curve upward, which means now it may be able to hit the top plate. But what I can do is I can tune the magnetic field just right, or at least the velocity just right, so that this thing is actually going to move through these two plates with zero net force. This is what we call a velocity selector. What a velocity selector does is it allows us to choose charged particles moving between these plates with a certain velocity. Because any other velocity, if it's smaller than that velocity, it's going to curve down. If it has a higher velocity, it's going to curve up. So I'm going to have a particular velocity allowing this thing to move through undeflected. So let's talk about that one. So in this case, what we want is that the total force, i.e. the Lorentz force, is simply equal to 0. So let's take upward as our positive y direction. So here I'm going to have the magnetic force minus then the electric force is equal to 0. So this is going to be Q times V times B, because the angle between the two is simply 90 degrees, minus the electric field. Since this is equal to 0, I can then divide everything by the charge. That guy's simply going to go to 0, which means then that the velocity is simply going to be equal to the electric field divided by the magnetic field. As long as I have charged particles moving through my plate with exactly this velocity, which is the ratio of the electric field to the magnetic field, I will then have 0 net force on these guys. It's not going to curve up and it's not going to curve down. So if I ever care about knowing exactly what the velocity of a charged particle is, this is one way that I can do it. I can simply look at this guy and determine exactly what the velocity is. Now, when's the situation I might care about doing something like this? Well, one situation is what's known as a mass spectrometer. Something used highly in chemistry. What's a mass spectrometer? Well, mass spectrometer is an external region of magnetic field. So let's say here my magnetic field is pointing out. So what do? Well, you take a charged particle, you put a little window in here. So we're going to take a charged particle with charge of Q, cause that to move with an external velocity or magnetic field, let's say this way. So this thing is moving with a velocity. It's going to enter this region of magnetic field. And then this thing is going to what? Curve, right? So as this thing moves inside, I point my fingers in the direction of the velocity, curl towards the external magnetic field. So I have to rotate my palm this way. It's then going to feel a force down in this direction. So after this thing moves in, it's then going to curve and hit something like this. So what? Well, typically what we do is we put down here detectors. What the detector does then is it measures where this thing actually hits, which means that we can measure actually the radius. So the distance from here to here would then be the diameter of the circle, which means we cut that in half. That's then the radius of the circle. So from here, we can actually then measure this radius r. So again, so what? Well, again, we know the only force acting on this is going to be the magnetic force. So here I'm going to have V times B times Q is then equal to mv squared over r, or uniform circular motion again. Again, the V's are going to cancel. So from here, I can measure something like the mass of this charged particle. So this is going to be Q times B times R divided by the velocity. This will be our mass. So if I wanted to measure, say, particular properties about this charged particle, in this case, the mass, hence why it's called the mass spectrometer, then as long as I measure the radius and the external magnetic field, I can then determine the mass if I know the velocity. How do I know the velocity? Well, we use a velocity selector. So again, what we're going to do is we're going to put parallel plates here, set up an electric field, which then points in this direction. Oops, electric, not magnetic. There we go. We can use the same external magnetic field if we want to. So in this case, the magnetic field would point this way. Sorry, actually, electric field has to point the opposite direction. There we go. So in this case, I can actually determine exactly what the velocity is by first letting it go through a velocity selector, allowing me to then control what the velocity of this thing happens to be. So in this case, we now know the velocity is simply equal to the electric field divided by the magnetic field. So finally, we get that the mass then is equal to the charge times the magnetic field squared times the radius divided by the electric field. So this is a mass spectrometer. So one very important application of these velocity selectors would then be this. Another important one is the determination of the electron. So way back in the 1800s, J.J. Thomson discovered the electron. So he made the discovery of the electron. The way he did this was actually using a velocity selector. So basically what he did is he took a cathode ray tube. Here's my cathode ray tube. Put a big old bubble on here with an external magnetic field. And then what he did was he applied a huge potential difference across here, delta V, causing these electrons to accelerate. So they were going to accelerate basically in this direction. But he also put this into a velocity selector. So this had an external electric field, say pointing this direction. Magnetic field out here pointing this way, electric field then pointing this way. So he could control then the velocity of these electrons. So when these guys came out, by the time they get into this region, they then curl in this direction, undergo uniform circular motion. From here, you can then apply this equation we just came up with here to find what's known as the mass to charge ratio. So basically, this experiment allowed him to verify that there is something called an electron, and he could determine then the mass to charge ratio by knowing the external magnetic field, measure the radius of curvature at which these things were deflecting, and the electric field. The other portion, which finally allowed us to determine the charge and the mass of the electron, came from what's known as Millikan, the Millikan oil drop experiments. What Millikan did to finally determine the charge of the electron from the mass was he took parallel plates, took oil, little oil droplets which happened to be negatively charged. In this case then, what he ended up doing was setting it up so there was an external electric field pointing this way. And as he put the oil in here, he would then tune the magnitude of the external electric field such that the net force then acting onto the oil would be 0. Because here what would happen is then you would get an electric force pointing upward. You end up with a gravitational force pulling it downward. From here, you can then determine the charge of the electron from here, because what he found was that by doing this experiment, the charge was always proportional to some constant times 1.602 times 10 to the minus 19. From there, he determined exactly what the charge of the electron was. From that charge of the electron, you can then plug it back into the charge to mass ratio to then determine the actual mass of the electron. So the overall point is, if you grew up in the 1800s, you would have won probably a Nobel Prize at this stage by knowing as much physics as you do right now, which would have been awesome. Unfortunately, it's not the 1800s anymore, so we kind of ran out of our luck a couple hundred years ago, but that's fine. So, anyways, we'll leave it there for now. We'll do one more example on Wednesday, and then after that, we'll start talking about what happens if we put a loop of wire carrying the current in an external magnetic field. I'll give you a hint. There's going to be a torque on it, so we're going to go back to torques. Okay. So I'll see everybody for lab later. Oh, yes. Fair enough.
Okay, so
and 3.3 there.
Maybe that's why I was like, how would so okay, so that'll be way different. That was like, then I don't know.
Why are you calculating resistance? So here you should be calculating using those resistances, the current and the potential. So the things that you took the data off of. And then you're going to compare between your theoretical and your experimental. So you should be calculating. No, that is the potential. The currents. So that's what you need to calculate as well. So you need to calculate these guys theoretically as well as these guys. And then do discrepancies between all.
I don't know why this is like somewhere all this.
Okay.
We just don't. So like I should know what's going on. I don't.
Okay, give me 1 second.